Awesome. Okay, welcome everybody to the type session. Our first speaker for the session is Brigitte Pientka, who is going to be telling us about a dependent type theory for metaprogramming with intentional analysis.
Right, thank you. So this is joint work with Jason Hu. This is, in fact, the work he did in his doctoral thesis. He defended in November, and he wasn't able to come today. But my understanding is he's online, and he's hanging out on the Discord channel. So if you have any questions after the talk, feel free to touch base with him. So the first thing maybe we should agree on is what do we mean by metaprogramming in this setting? Okay, so what I understand here in this talk about metaprogramming is that we want to write programs that produce other programs. And we'd like to also manipulate these programs within the same language. So typically, metaprogramming systems support at least 3 of these operations, but we also want to support the 4th one. So the first one is essentially quoting a piece of code, a program, or an expression, and you get an AST back. So if you have x times 2, x is some kind of variable that is contained in this expression. Splicing, in our setting, we will bind this piece of code x times 2 to this variable c, and we want to use it here in a larger AST, where we then instantiate this free variable x with 0, and that gives us the expression y times y plus 0 times 2. Okay? And then we want to evaluate that expression, so we bind to this variable c this piece of code, y times y. We instantiate y with 2, and that will evaluate to 4. And last, we might want to do code analysis. We want to eliminate this pesky 0 times 2, which will eventually get away anyway. And we would like to maybe transform this expression into y times y. So metaprogramming is very popular. It's been a long history, and it's also popular in type theory. It's widely supported in proof of systems like Lean, Rock, or Acta. And there's a good reason for it, right? It eliminates boilerplate code. We can implement tactics. We can use proofs by reflection. So it is a good thing to have, right? But there's a but, okay? And the but is that when you look at these systems, let's say MetaCog or Lean or even Template Acta, some clever person, and I have a lot of admiration for them, they've implemented this facility quote, okay, which allows you to quote a piece of syntax that you wrote in this proof assistant, and it's being reified in a data type that is being implemented in this proof assistant. And that data type is something called like TM. It uses some kind of De Bruijn variables for modeling your variables. And in particular, it doesn't enforce anything such as well-scopeedness or well-typedness. And that is sort of like going against the philosophy, right? We believe types are good, and maybe we're even believing dependent types are even better. So why are we satisfied to have a representation of this piece of syntax as an untyped piece of syntax? So that means essentially if you have errors in your code generation, you catch them later on, not at generation time, but when you use them. But maybe more from a fundamental point of view, I would like to know what is actually that type theory we're using, right? I mean, it's not the calculus of construction, or it's not Martin-Löf type theory. It's actually this thing, right, that has also quotation in it. And I'd like to know what is that theoretical foundation. So that's the central question we were setting out in this work. What is a dependent type theory for metaprogramming that allows us to quote objects that might be open, that we can compose code objects, that we can recursively analyze these code objects, and we can evaluate them. And these code objects are well-typed. So let's look at a few examples, okay? So here's a very simple, simply typed example. We're doing multiplication generation instead of power today. Okay, so you get an input nat, and you want to generate code that will add x n times. So if you have 0 as an input, then you generate the code of 0. If you have successor of m, you first generate mult of m that will add x m times. And then you splice it in. You rename the possible variable in that piece of code u with x, and you add x to it. So in the type theory, we also want to know what kind of equivalences hold. Okay, so here we have mult of 1 that would evaluate to this expression 0 plus x, this quoted expression. But it is a different abstract syntax tree than just having x. Okay? And mult of 2 will evaluate to something like 0 plus x, but it is, again, a different expression than x plus x. So when you run this code, okay, then you also have certain equivalences. So for example, here you would bind mult of 2 to this expression 0 plus x. You instantiate the x with 5, so So you're actually computing 0 plus 5 plus 5, which gives you 10. But you can also use code underneath a binder. Okay, that's the second example. So here we're renaming the free variable that is in this piece of code with y. So we get 0 plus y plus y. And since in a type theory we're evaluating under lambda, this would actually then give you a function that adds y to y. So, and the last operation is we want to do code manipulation. So we might want to get rid of these pesky 0 times something. So here we're writing a code transformer. It takes in a contextual object, okay, where we have here an object nat that depends on this variable x, and we're returning a nat that depends on x. And we can analyze what the shape of y is. For example, it is 0 plus b, where b is our pattern variable, and in this case we return just b. And if we have a plus b, where both of these are pattern variables and might contain x, then we first simplify a, and then we splice it back in. And yes, there's sort of this renaming of this variable happening, so we are in a good world. Okay, and anything else, we just return. So then you can actually simplify your multiplication code, and you get this equation that indeed the simplified multiplication algorithm of 2 will be equivalent to x plus x. So, so this is essentially the goal of this Martin-Löf type theory. It uses as an idea layers. It's based on these ideas of contextual types. When we quote an object, we get a well-typed contextual code object. When we compose well-typed object. We can run well-typed code as programs, and we can pattern match on that code. So the key idea is really that we have layers. Okay? So the first layer is the layer of syntax, and that is code. In our case, really the syntactic representation of Martin-Löf type theory. There's no computation. So if you define nil, okay, which is a polymorphic list constructor, then you can define nil, which needs to apply to a type. So here you have lambda x applied to nat. And that is not equivalent to the syntax of nil of nat because they're real syntax trees. Okay? Now you want to know what is the type of these objects. Okay? Well, clearly the first object has type list, lambda x applied to nat, because I'm just replacing the a by whatever type I had here. And the second object has type list of nat. But the question is, maybe on the level of types, we do want to identify these types to be equivalent, because in some sense, types classify objects, and they're not really just syntax. And so in our type theory, we do allow reductions on the level of types, but not on the level of code objects. Okay? So that brings me to the second layer, which is essentially the Martin-Löf type theory we know and love. It has computations, in particular has beta reductions. Okay? So it's really exactly what Martin-Löf type theory is. And then we have a third layer, which extends Martin-Löf type theory with the ability to quote objects, to compose objects, do recursion on these objects, and pattern match on these objects. So now you have really a tower of these languages. They share the syntax, more or less. Okay? Clearly, the meta-programming layer extends Martin-Löf type theory with these constructs we have. But we also want to control the computational behavior, the equivalences we have at each of these layers. So that's exactly what we do. We have uniform syntax. We have a syntactic typing judgment that essentially is parameterized by what layer we're at. So we can control these equivalences. So I give you a little bit of a flavor what this looks like. So this is a typing judgment. It is parameterized by this I. And this I is either code, a dependently type theory, or a meta layer. The gray part is coming from the universe levels we have to handle. Okay? And then usually in a type theory, you would say, well, T is well-formed, and then, of course, this type and this context is well-formed. And now the question is, are they always well-formed at the same layer? And the important observation is that since we want to distinguish what equations hold for code versus types, we actually think of the code, which is here in orange, right, that for code, we would not have equivalences, but it lives in this typing environment where we do allow equivalences to happen. And this function here essentially tells us how the object we're trying to type relates to its environment in which it lives. So when it's a meta-programming function, all of them are well-typed and well-formed at the meta-programming layer. If it's a dependently typed object, all of them are well-formed and well-typed at the dependently typed layer. Just at the code layer, we make actually that distinction. Now, the most important lemma we have is actually the lifting lemma. Okay? And that says that a well-typed object at layer I remains well-typed at layer J. And to give you an idea why this is important, I put up here the typing rule for pi type or for applications. Okay, so this is code. T applied to S. So S is code. Okay, S is of type capital S. But I said that this type here, right, here is actually is a dependent type, from our D layer, from our Martin-Löf type theory. So why can we use an object that is code on that layer that is D, that is sort of higher up? Okay, and that is basically justified by the lifting lemma. Okay, and similarly, for code execution, we have here a piece of code that is C. Okay, but we're plugging it into an expression that comes from our M layer, where we have pattern matching and recursion and everything. And so why is this justified? Well, again, because we can promote or lift C up to that M layer. Okay. So this is really, really central to make this work in some sense. So our main contribution is then that we have a syntactic type theory with a non-cumulative Tarski-style universe hierarchy that supports quotation, composition, execution, and recursion of these type theoretic code. We have a uniform syntax. We have this layer that we have. So here we have 3, C, D, and M, and that allows us to control what equivalences will hold. We've proven weak normalization and the decidability of convertibility based on a Kripke logical style relations. So we define a reducibility candidate, very similar to some of the previous work, some of our own, but also from Andreas. And in order to control sort of the complexity, because we have now 3 different layers and we don't want to do like 3 different kinds of normalization proofs necessarily, we introduced this idea of using pers. Okay, so that actually cuts down even Andreas's proof by half. Okay, so it makes it sort of manageable to do actually this proof. And we give some examples in the paper where we sketch sort of how we could use DeLaM to write tactics similar to the simplifier I've shown you earlier. So I'm really fast today, apparently. Okay, so you can ask lots of questions. If you think about the spectrum of metaprogramming in proof assistance, you have on one side sort of this untyped representation of code. That's sort of currently the state of affairs in Metacoq or in Lean or in Acta, as well as in tactic languages like the LTAC. And then certainly, right, we were gradually moving to something that is giving more guarantees. So LTAC2 gives more guarantees, MTAC gives more guarantees. But sort of what is this type theory that would give you really full guarantees, right, about the code you're writing that has been sort of elusive? And that's what DeLaM tries to do. So what's next? Well, the next is really to implement this kind of this type theory, maybe revisit our choice of Tarski versus Russell-style universes in our type theory, and develop maybe an NBE proof for this language so we can actually get a good mechanization out of this work. All right. So we have lots of time for questions.
Yeah. Okay. Thanks for the nice talk. Do you think that you could use the universes and sorts to emulate your layers instead of having an explicit layer mechanism and rely on universes instead?
I don't think so, because of the fact that we want to control equivalences. So unless you can also control the equivalences somehow by the universe layer levels, which typically we don't. Typically, we have the same kind of equivalences, regardless of what universe level we have. I mean, if you could, then I would say yeah. I'm hopeful.
I was more talking about sorts than levels. Like, if you have a sort prop, then you have impredicativity. If you have the sort S prop, then you have proof irrelevance. So there is some kind of new equality, and you could have less as well.
Yeah. So we would need to change probably the notion of equality, and then I think one could maybe emulate them. Yeah, that is true.
I was wondering if you thought at all about extending this to sort of arbitrary layers of metaprogramming so that you could have one metaprogram generating further metaprograms in the next stage, similar to, say, the staging in something like Racket.
Right. So in this work here, we were really trying to emulate or understand what the current practice of metaprogramming in proof assistance like Lean, for example, is. And there you really have only 2 layers. Okay? Now, we've done some other work, in particular Jason has done some other work where he has a modal dependent type theory which has n layers, but it doesn't have pattern matching. Okay? And so the important part when you do pattern matching is, I think, a form of layers because it gives you a very clear characterization of the syntax of the thing you're pattern matching on. Okay. So in fact, I would say it is essential that you have a notion that controls that. And by restricting it to 2 layers, you get that control. Okay. Now, I should also mention we had a paper at ESOP, okay, where we describe a simply type version of this layered system. And there we do sketch an n-ary version. Okay. But if that is really useful in this setting, I'm not sure. Okay.
Okay, so just as a follow-up, it sounds like and I think this is what happens in practice in something like Racket, which is if I want n layers, I'm always working with 2 relatively. Like I'm always at 0
Yes,
and 1 relatively.
that's right.
Okay, thanks.
Yeah. And I would say actually a lot of programs where you want n layers, you can, if you have pattern matching on code, you can do the optimization you would otherwise do in multiple layers. Okay? So I'm not 100% convinced that it's always useful to have n layers in the theory. Okay? Because if once you have pattern matching, you can analyze the code that you have generated and you can optimize it. So one thing, for example, you might want to have multiple layers because you know that in the first layer you get a matrix that has zeros in it, and then you want to optimize, like depending on what the second argument is, you could optimize sort of certain multiplication or operations later on as well. But then let's just generate them, and then you pattern match and eliminate. Okay. So I think there is something to be understood about this trade-off of writing your own program transformations versus doing n-stage multi-stage programming. You see what I mean? Yeah.
Hi. Speaking of pattern matching, in practice, we usually need different notions of equality for different purposes, right? Sometimes you want to match the syntax really on the nose. Sometimes you want to match up to alpha equality. Sometimes you want to match up to definitional equality. Can you see that being integrated into this framework as well?
So our experience is you basically have to make a decision, right? So in this work, we made this decision that what code is pure syntax. So there's you get alpha equality, but no other definitional equality. Okay. Now we have a paper at JFP, okay, where we made a different decision, and some of the reviewers didn't like this, okay, where we do allow definitional equality on the object that we're generating, okay, and I think that is perfectly fine, especially if this is just thought as a black box generation. If you want to do pattern matching, though, I think you want to know what the syntax is you're getting that you're pattern matching on. And so I think there is a good reason that if you want to support pattern matching, that you don't want to normalize the code that is inside the box, okay? And that, because you can always write it, if you have pattern matching on code, you can write the normalizer. You can write the weaked normal form if you really want to put it in a weaked normal form. So yeah, so I think there's this trade-off, okay? And I think a lot of it has to be decided once you actually want to use it. But for pattern matching, I do think you want to know the syntactic structure of the thing you're pattern matching on.
Okay, that makes a lot of sense. Thank you.
Okay, let's thank Brigitte again and switch the projectors.